Start.
Hi, this is Ishita and our team members Kalyan, Raja and Mamata. And this today, we're gonna speak more about our demo presentation on our project, which we have been done from the past few months, which is ship your critical section, not your data. Let me give some time to introduce themselves. Kalyan and Mamata, you can.
Hi.
Hi all, this is Mamta Edvelli.
Hi, this is Kalyan. So we're gonna present the title called "Ship Your Critical Section, Not Your Data." The main idea here is transparent delegation. Me and Mamata gonna start that. Me and Mamata and Ishita gonna start that. Yeah. Over to you, Mamata.
Hi everyone, this is Mamta Edvelli. As you all know, we are giving a presentation on our code implementation and what we have achieved, implemented here.
Kalyan, can you please screen share?
Yeah. Krishna.
Yeah, thank you. We are gonna moving forward. I'm gonna discuss more on shipping your critical section, not your data, enabling transparent delegation with TCLocks. So the major idea here, what exactly the project goal and everything is. We have been working on multiple threads these days, and we are having facing an inconsistency on all these things. So logs are widely used synchronization mechanisms in concurrent applications actually. So can you go for next slide? So usage of logs has been drastically increased in the Linux kernel where more logs are used to improve the scalability. So for example, the basic idea behind this TCLocks is it gonna calculate the number of threads versus the millions decreases its count. Now, speaking on to the algorithms which we worked on is spin log, blocking log, and read writer log. So if we have been a major keywords which I have been telling from the past few minutes is critical section and transparent delegation and TCL logs. What exactly the critical section is? The critical section contains all the major data within the API where it gonna be working on with the particular data to move forward for the next threads. When it comes for the transparent delegation, it is like using a standard lock and unlock APIs without rewriting the entire code. And it is a kind of minimal shared data movement. For example, to speak on, instead of executing the entire code, it start executing the part of code which is majorly important to proceed forward. And coming to the TCL logs, it reduces the data movement and the context switching. The major idea is like minimal shared data movement. When it comes for the spin log, I'll give it just a few words like what exactly the spin log blocking log is. Spin lock is a log that causes a thread like trying to acquire a lock and waiting in loop. Like it repeatedly keeps on checking if the lock is available or not. So what happens in this case is the CPU time is wasted. Along with that, the threads keep on checking. So it should be always in the active state in spin lock. There were some or other times it is not much flexible. When it comes for the blocking lock, it some or other point it covers major disadvantages of spin lock where it makes the CPU time more efficient. Like blocking lock will put the threads attempting to acquire lock into the sleep state until the lock is active. So the less cycles are get wasted in blocking lock. When it comes for the read writer lock, multiple threads can have read access at the same time simultaneously, but only the write access can be done by only one thread. So even for going ahead with the write lock, initially it should wait for the read locks to release all the locks and then do the write operation on it. And in the critical section, it would be only one thread which gonna come into the same time. And coming to the TD, like transparent delegation as well, it works on the same. Application code doesn't need to rewrite for the lock management. Can we go for intro? Yeah. As I spoke earlier, like locks are widely used synchronization mechanism in concurrent application. There you can see the visual representation. If the shared data movement is high, the CS execution time is high, and the application performance is drastically goes down. So why exactly we have been working on locks is it improves the scalability and it depends upon the threads and their operations, and it majorly works on optimizing the critical section. And this TCLocks is highly used for high computing environment with a minimal rewrite code for the application developer. But in reality, if we have been working on the minimal rewrite, it is some or other point it is kind of not flexible too. Can we go for next part? So now I'm gonna discuss major ideas behind like the log designs. We have a traditional log design and delegation style log when coming with the TCL logs. So traditional log design, what exactly the flaws and how exactly is. Here application developer writes code within the log and unlock API. If three, for example, I have been given an example for three threads. If one thread acquires a lock, it goes into the critical section. I'll just give you an overview what exactly it happens here in the traditional log design is. We have one thread, it enters into the critical section code and it accesses the shared resources and then it calls the lock API, and then it sees whether the lock is available or not, and then it moves forward to critical section and it works on the operations of the shared resources and then goes for the calling unlock API and makes other locks available for all the other threads. This process goes on for entire threads. It is a kind of inefficient way to speak upon. The major drawbacks comes with the contentation and the throughput. So application performance gonna suffer, threads forced to wait, and the data movement is also very high here. So data always accounts for like data, like moving forward, it gonna be more not insufficient. Can we go for the next slide? So traditional log design failed to provide, like what exactly the drawbacks why we aren't moving with traditional log design is, it's locality of shared data. Like what exactly the data locality is, accessibility of data being used by processes. So if you have a like a good idea what exactly and which process is executing and which thread is working on, you could have a good idea on it. And no application performance is not an idea here. It's not that good in traditional log design, and the shared data movement is very high in terms of application performance goes very low, and the critical section execution time is also very high. If you see the visual representation here, and first initially the log goes here and then count plus plus is nothing but the critical section, and then it goes for the shared data movement and the log get transferred to the thread 2, and again it goes for the similar process. That's how exactly. Moving forward, we have a delegation style log, so Kalyan gonna be explaining more on this.
Delegation style logs. As we have seen, traditional log designs fail to provide locality of shared data. So this technique, delegation style logs, has like we ship the critical section instead of the shared data. So it ships the critical section request in the form of a function. As we can see here, it is in the form of a function, which is an increment function, and send request to server function. So this function is sent as a request to the server thread. The critical section, which has incrementing share counter, does the function here. So as we see, this is a client server model, and server holds the server access a lock holder, and the critical section execution time is increases with the core count in the system. So this is the main functionality of delegation style logs. Let's go deep into delegation style logs. Here we can see the server thread and the client threads. So after the execution of the server thread critical section, the uh, critical section of the thread 2, which is the client thread, request for the server thread, and after some spins, after some wait, the server thread execution, the client thread critical section execution will be completed, and will get the response. Same goes with the thread 3. So this in this way, the delegation style log works. So this delegation style logs has a drawback, which is called the application modification. As we have seen in the above slide, uh, the client thread has to do some modification to follow the dedication style lock. So if we have large applications, the app modification will be really tough. Practically it is impossible to use dedication dialogues for complex applications with more number of code lines. So we have introduced TCLocks. Main idea of TCLocks is transparent delegation. We will use here transparent delegation, which means transparency while using delegation style lock. So transparency means that use of standard and lock and unlock APIs rather than rewriting the whole applications, so that minimal modifications of the code is required. So delegation means we have like seen in the above delegation style logs, which is minimal shared data. So going deep into the TC log concept, it only captures the thread context within a critical section. The server impacts on waiter thread during a critical section is very low, and also we'll use general purpose registers, stack pointers, and instruction pointers here. Now coming to the mechanism or TC-lock concept, here the thread capture lock and unlock APIs to prevent the context changes in the lock acquisition. We will maintain thread in queue. So for the first head of the queue acts as the server, and the remaining acts as the client. So there is like no dedicated server in that, but the head of the queue acts as a server. So it becomes a server and execute the critical section, and then it transfers to the thread 2, which is the remaining threads in the queue. So it uses nested locking and out of order unlocking. The queue based locking, which is the list of waiters maintained as a queue. uh, in this way, the mechanism of critical section in TC log works. So after the execution of the server thread, the next thread will be executed, which has the spin. At the same time, thread 3 also spins, waiting for the critical section. And after it is switched to thread 2, it looks like this. After the execution of thread 3, then the server will notify that yes, I have executed your critical section, you can go to your non-critical section. So external events can modify the waiters content. This is one of the waiters context. This is one of the drawbacks of TCLocks, but it acts as very low. Actually, interrupts are required during stack access. For this, we are using a femoral stack, which is an empty piece of memory used during critical section execution, and also which handles waiters CPU time. Next, coming to the main code here, when the thread attempts to acquire the lock and find is occupied, it prepares for encapsulation in the critical section in like a queue node. I'm saying like it maintains as a queue to as we see here, the acquire lock function. It has parameters as lock API and also critical section function as an input. So it takes the inputs and execute the critical section while acquiring the lock. So we also have this combiner execution the critical section while all waiting threads in the queue. So this function is called as execute critical section, taking input as a lock. While taking input as a lock, so if the lock is available, the lock variable is true. If the lock is not available, the lock variable is false, and the releasing of global lock will be acquired after processing this function. So next, coming to the spin lock function. This is a main function which encapsulate critical section to execute. The we have a global lock flag and also the tail of the queue here. So while executing this in the virtual machine, these are the statistics which we have got while executing this. So while executing the critical section, this is the disk IO probability and also the network traffic and the memory use. The memory use is constant, as we can see here, and also the CPU usage is varying, depends upon the function and the program we have executed. So here we can see this is one of the main function. Here you can see the program output, like task 1 acquire the lock and task 1 release the lock. We have just inserted the oh, print statements between acquisition and releasing of lock. So this is the output we have got, as you can see the visualized output here. And if you see here, the execution time, the waiting time, the work ID, and the zone ID of the task or thread completed here. And here this the thread one. So here we can see the mutexes which encountered while executing the program. So this is the main programs which we have done, and the presented output is here. So VM we have used is operating system Ubuntu uh, 20.04, and the kernel version here is Linux 5.14.16 with hyperthreading disabled. So these are the outputs which we have got while executing the programs. So this is about the concept and the program and the output. So the evaluation part will be explained by Mamata.
Hi all. Now I'm going to discuss how we evaluate TCLocks. To effectively assess TCLocks, we need to answer questions like, does TCLocks reduce the time spent in critical section? Does TCLocks improve application performance? I will provide the answers as we proceed to the following slides. More than 4 threads show minimal shared data movement, enhancing efficiency. With four or fewer threads, significant context switch overhead and inefficient batching reduce performance. Our findings clearly show that TCLocks reduces the time spent in critical sections, enhancing efficiency and improves overall application performance, thereby increasing throughput and reducing latency. These results depicted in the graphs confirm that TCLock significantly outperforms traditional locking mechanisms, answering our initial questions positively and demonstrating its effectiveness in high concurrency environments. Next slide, please. In this slide, we explore TCLocks through benchmark test and real-world application analysis to assess its effectiveness further. The micro benchmarks conducted within single sockets, as shown in the graph, show minimal shared data movement, demonstrating TCLocks efficiency in environments with the tightly coupled processes. When expanded across multiple sockets, TCLocks efficiently handles NUMA-aware policies, which is vital for performance in distributed computing systems. Additionally, in real-world applications such as databases and server environments, TCLocks significantly reduces context switch overhead and improves data locality, leading to enhanced overall performance. These results confirm TCLock's superior performance over traditional locking mechanisms in varied high concurrency settings. Next slide. This slide presents findings from comprehensive evaluations conducted in user space applications like LevelDB and kernel space settings such as Metis project. The results indicate that TCLocks not only matches but often exceeds traditional lock performance across various thread counts, showcasing its robust adaptability and efficiency. Especially in LevelDB, TCLocks achieves up to 5 to 2 times improvement in throughput compared to conventional locking mechanisms. These significant performance gains highlight TCLocks' potential to revolutionize how critical sections are managed in modern computing architectures, ensuring minimal latency and maximized throughput even under extreme workloads. Next. And this slide brings us to the conclusion of our discussion on TCLocks. Throughout this presentation, we have explored the challenges of traditional locking mechanisms and introduced TCLocks as a transformative solution designed to enhance efficiency and performance in multi-threaded environments. From the initial conceptual overview to detailed performance evaluations, we have seen that TCLock significantly reduces critical section time and improves overall application performance as demonstrated by tests on systems ranging from micro benchmarks to real-world applications like LevelDB and Meteors. The performance gains observed affirm TCLocks' potential to provide transparent delegation without the need for extensive application modifications, offering a practical and scalable solution for today's high concurrency computing needs. Thank you all for your attention and thank you.
Thank you.
Thank you, everyone.